Good morning, folks. How are you today? Before we begin, let me back up a little bit and talk about what we have done so far. So, in the beginning, we learned how to find root of a function. Then, a little later on, we learned how to integrate the function with respect to x between limits a and b. Now, last week, we learned how to take any ordered derivative of a function with respect to x. So when I said we found root of a function, we can basically find any property of this function. Now we can also integrate it and we can differentiate a function. So we can do all the things that we might want to do or know about functions. And that becomes very, very valuable because we can do each of these things numerically. So now let's take a look at our 4-bar linkage and see where we can apply the ideas that we have learned so far. Actually, before I move on, let's see something more here. Here we were trying to find x. So when we are trying to solve for x from this equation becomes an implicit equation. Whereas in this case, we know everything on the left-hand side, so we just did a sequence of calculations and got our answer. So this was an explicit type of an equation. Same here, this is an explicit type of an equation. We do a sequence of calculations to find the derivative, and we get our answer. Common mechanisms that you are going to see is a 4-bar linkage, and I'm going to show you lots of examples. But what you might like to think about as you walk around, get out of the door, get in your car, turn the wipers on, you will see 4-bar linkages everywhere. So maybe for the next 1 week, you might like to identify where there is a 4-bar linkage in a everyday use. So what is a 4-bar linkage? So here is example of that. Basically, we have 4 bars that are linked together using these pins. Now, some of these pins can be fixed, whereas some can be free to move in space. So in this particular case, we are looking at a particular type of 4-bar linkage called slider crank mechanism. So this is just one of the subtypes of 4-bar linkages. We'll see others in a moment. So what we have here is we have 2 pins that are fixed. Imagine, even though there don't need to be any bar D, but imagine there is a link D because that will tell us the distance between these 2 pins. Then we have this bar which can rotate about on this pin, and from x-axis its angle is theta. We have another bar, again this can rotate, move, and it makes an angle of beta with respect to x-axis. Then we have a third bar, C, connecting this one, and it makes an angle phi with respect to x-axis. So what we want to do is we think about one as being driver and other as being propelled by it, but it doesn't matter. It can be the driver or this can be the propeller. So what we want to know is if we change theta, what should the angle phi be? So for a given angle theta, what should angle phi be? So let's go ahead and look at this 4-bar mechanism. So here are 4 major types. One is this called drag link. In drag and link, the lengths are such that S plus L is less than P plus Q. So in this case, this bar or this point rotates on a circular path with a radius of L, and this bar rotates in a circular path with a radius of Q. So both have continuous motion, full revolution for both links. Here, when S plus L is less than P plus Q, but there is a continuous motion in the sense when we rotate this, this one just rocks. So it rocks a certain angle, and that depends on the length. Here is a double rocker. So here S plus L is greater than P plus Q. So if this one rocks as well. So not full revolutions. And finally here S plus L is P plus Q. So both of them rotate in shape of a parallelogram. So they always form a parallelogram. So that again we have a continuous motion. So I'm going to show you examples. I have 5 example videos. I'm going to stop after each. The first one is the bicycle peddler. Okay, so you saw a very interesting 4-bar linkage example when a person is pedaling on the bicycle. Now let's look at the next one of a knee joint. Okay, here is another one which is of a parrotfish jaw. By the way, I have not been identifying which of the 4 types of 4-bar linkages each of these were. So you might want to identify on your own, if this interests you, what kind of a 4-bar linkage it is. So these are all very short videos. As you see, I'm going to show the next two, one next to each other without my narration in between. Okay, so you saw a lot of applications of 4-bar linkage. Now let's try to understand the math of it. So let me draw my diagram from here. So here is our x-axis, y-axis, and our 4-bar linkage. So we are going to start from this point. This is our vector A, this is our vector B, this is our vector C, and this is our vector D. So that would mean when we add all these vectors, A plus B plus C plus D, we should get back to 0. Okay. This angle is theta. This angle is beta. And this angle is phi. Okay. So what we are going to do is we are going to write this vector equation in its xy components. So we see we have vector A. If it is at angle theta, its x component would be A cosine theta. If we have B at an angle of beta, its x component would be B cosine beta. But now the C is pointed downwards this way. So now when it is at angle phi, its x component would be negative. So we will write C cosine phi, C cosine phi. And D is just horizontal, so we'll just write plus D is 0. Okay, let's look at y component. For A up, A sine theta. For B up, B sine beta. And again for C, it'll be negative. So minus C sine phi. And D has no y component. Okay. So what we can do is we can take B cosine beta out of the first equation. And we will get C cosine phi minus A cosine theta minus D. From second equation, we will get B sine beta. So we will get C sine phi minus A sine theta. Okay. Then what we are going to do is we are going to square both sides and add these two equations. So when we add these two equations, we'll have B cosine square beta plus B square sine square beta. So we'll just get B square. And then when we expand these squares, so you can see we'll get C cosine square phi, C sine square phi. So when we add them, we'll get C square. Same way, we'll get D square. Same way, we'll get A square. Then now we will have the compounds. So we'll have D and C. So D and C. So we'll have 2DC cosine phi. Then we will have C and A. So minus 2CA cosine theta cosine phi. So we'll write cosine phi cosine theta. Okay. So remember this has three terms. So there'll be three of these. So we have done D and C, we have done A and C, we have to do A and D. So we will have A and D will become plus 2, that is the last term on my slide, dA cosine theta. Okay. Then we'll have two terms from these. Our first term would be minus 2ac sine phi sine theta. Oh, one term only, sorry, one term. So we have a total of CD squared, three terms, 4, 5, 6, 7 terms. Right? Now what we do is we define some ratios. So one ratio we define is R1, which is D by C. Another ratio R2, which is D by A. And a third ratio R3, which is D square plus A square plus B minus B square plus C square over 2CA. So when we do these substitutions in here, our equation simplifies. Because notice this, all of these are included here. So we will get a simple equation R1 cosine theta minus R2 cosine phi plus R3 minus cosine theta minus phi is equal to 0. So if we know R1, R2, R3, which are basically link length ratios, then our only unknowns are theta and phi. So we have a equation. Let's suppose we want to find phi, but use theta as a parameter. We want to solve this equation. And this is a transcendental equation. So in the past, 20, 30 years ago, when we used to teach 4-bar linkages, we would derive this equation and then only for one specific case, one specific theta, solve for phi. But now that we have computers available, we can do wonderful things. So not only just at a given theta, we can find phi. Once we start rotating it, we can say given d theta dt, what is d phi dt? Imagining this to be a constant. Or even if we have angular acceleration, we can include that here. And we can find also angular acceleration. So given all these quantities, if we know angular position, velocity, and acceleration, for the other linkage, we can find its position, its velocity, and its acceleration. So here, what we are going to do is we are going to use all of our procedures. So in fx is equal to 0, you learned that best method is Newton-Raphson method. And next best, if you don't want to take derivatives, is secant method. So what we are going to do is we are going to solve our transcendental equation using secant method. So once we have solved that, then we would need derivatives. So for derivatives, remember we have learned to find any derivatives. So we will use numerical differentiation. Now you'll see when we go through numerical differentiation, we'll be unsure what kind of precision we have. So what we are going to do is we are going to find these derivatives at two different spacings and then do Richardson extrapolation. And remember, you learned Richardson extrapolation during numerical integration. But now we are going to apply it to derivatives. So this is going to be the problem that we are going to solve in today's class. And also you are going to be doing it as lab 11. So follow along carefully. So here is our example problem. Let's suppose A is 1 inch, B is 2 inch, C is 2 inch, and D is 2 inch. Then we can generate these R values, these ratios. And these ratio values come out to be R1 is 1, R2 is 2, and R3 is 1.25. So let's suppose we move the link, which is at an angle theta, at an angular velocity that is constant of 100 degrees per second. Then what we want to find out is same. We want to find out at a given theta, we know the velocity, this is 0. So remember, this is 0. So we want to find what is phi, what is d phi dt, and what is angular acceleration. So if we want to find d phi dt, what we can do is we can divide both sides, divide and multiply by d theta. Right? And then what we can write is we can write d phi dt. Remember, we multiplied and divided by d theta. Now we use this, we say this is d phi d theta times d theta dt, right? Now, if we want to take second derivative, so second derivative, what we are going to do is we are going to take d by dt of d phi dt. That's our second derivative. That's our d square phi dt square. So we differentiate this. Well, remember, this is omega. So omega is constant. And then we are going to take d by dt of d phi d theta. Right? Okay. So again, we multiply this by d theta and divide by d theta. So when we do that, what would we get? So again, we take this and this together, right? So we'll get omega times second derivative of phi with respect to theta. So we'll get omega square d square phi d theta square. Right? So we have our formulas. So that means once we find phi, we would need these numerical derivatives. So we would need first derivative of phi with respect to theta and second derivative of phi with respect to theta. Okay. So we don't know phi as a function of theta. So we need to solve that transcendental equation, that parametric equation. Okay. Okay. So as I said, you're going to do this for your lab 2 for Monday. So what you might want to do is pause here and create this spreadsheet template and follow along with me. I am serious. Please do write down what I say. Otherwise, some of you might get lost. So pause here, prepare a spreadsheet template, then follow along. I'm going to fire up my spreadsheet template. And here I have it. Okay. So I am going to start naming my cells. So let's see, I should have a cell name. Oh, before we go on the cell name, let's talk about our Visual Basic modules. Okay. So I have two Visual Basic functions in this module. We want to solve this parametric equation, function of theta and phi is equal to 0 by secant method. Remember, theta is our parameter and phi is our unknown in this case. So we'll have function f, theta, and phi. Remember the equation we just derived. So I'm going to copy it here. This is the equation we derived. Okay. So I'm going to copy it all over again. So our function of theta and phi, we separate them by semicolon because one is unknown and one is parameter. So this is parameter that is unknown. And let's go back to our slide. So our equation was R1 cosine theta minus R2 cosine phi plus R3 minus cosine of theta minus phi is equal to 0. So remember, we are putting both in degrees. Okay, that's how we are going to input from Excel. We are in Excel, we are going to work in degrees. But Visual Basic works in radians, cosine and sine. So what we are going to do is we are going to define a ratio to go from degrees to radians. We are going to say our multiplier is pi over 80, right? Pi over 180. So in Visual Basic, we'll write it as application.pi over 180. So that's my first line, right? So when we want to multiply or convert theta, so let's suppose theta is in degrees. If we multiply it by this ratio d to r, now p is in radians. Okay. Same thing, phi we will call p, we'll multiply degree to radian, and now p is in radians. Okay. Then what we are going to do is we are going to import R1, R2, R3 from the worksheet named slider. So these are going to be our named cell values. And then of course our function is simply R1 times cosine of theta. Now remember, T is in radians, R2 cosine P, phi is in radians, and this is theta minus phi in radians. Okay, so that's our function calculation. And then of course, you remember dx secant, it has got these 4 arguments, and we will get dx for secant method. Okay, so let's start naming names. So our this R1, we are going to say R1. This is R2. This is R3. This is EAPS. And we have omega, which we don't need right now, but we'll kind of leave it hidden up. So just to solve our transcendental equation, we need these 4 values. Of course, since our method is secant method, we'll have a start flag, so another name. We need 2 guesses. So we have x1 and we have x2. So let's change these names. So we'll call this x1 to be consistent. We'll call this x2 to be consistent. Okay, let's delete all this stuff. And then of course we will need our spacing h. We'll make it 8 degrees apart, so it's called h. So these are our names. Now let's start putting our numbers and formula. So first of all, we were given in our problem statement, R1 is 1, R2 is 2, R3 is 1.25. We want 6 correct decimal digits in our answer. So that's our EABS. And initially we'll make start false. And our initial guesses when theta is 0 is x1 is 30, x2 is 40. This is phi guesses, phi values in degrees. Okay, so I'm going to come to H10 in a moment. Let's start with this one. So if we are at the beginning of the iteration, start is equal to false, we will say this value is x1. Otherwise, we want the x2 value, which is in cell C12, to go there. So otherwise, C12. Okay. If start is equal to false, we'll take x2 value. Otherwise, we'll take value from x new, which is G12. So we compute the function. Remember, first is theta and second is phi. Function theta and phi. Now we are going to invoke our dx secant. But if you remember from our parametric study, we don't want those value errors. So we want to use dx formula only if f1 is not equal to f2, so that we don't have division by 0. And then we can now call dx secant using x1, comma x2, comma f1, comma f2, and we get our dx. So I'm missing a parenthesis. Yeah. Okay. X new is x2 minus dx. And then for convergence, what we are going to do is, since we want to count how many converged or not, we are going to say if it didn't converge, we'll call it 0. If it converged, we'll call it 1. So we are going to put an if statement there. If our absolute of dx is less than equal to EABS, that means we have converged, then its value would be 1. If we have not converged, value is 0. So we have not converged, value is 0. Okay. Before we move on, let us check. Let's check, start the iteration, true. So obviously we have that circular error problem. So we do go to file, we go options, we go formulas, and we make it manual. Don't recalculate, but enable iterative calculation. We want one maximum iteration at one time, and we have made this a very small number, 1 times 10 to the minus 99. Okay, so remember now we are in a manual mode. So I press F9, one iteration, 2, 3, 4. So 4 or 5 iteration, I don't remember if I counted them properly, we converged. So everything seems to be working. Okay. So let's reset this back. So we'll reset this to false, F9. Okay. And let's even change back to our automatic calculation mode. Switch this off. Okay. All right. So now we want to go to the next step, 8 degrees. So for 8 degrees, what we are going to use, we are going to use this as our first guess and this as our next guess. So we are going to say if start is equal to false, use this as the initial guess. Otherwise, use from the same row. If start is equal to false, use this G12. Otherwise, from the same row, G13. And folks, that's it. We need to copy this down. And we need to copy these downs. All of these down all the way. Okay. So of course, none has converged, but you can see the chaining. 30 to 40, 40 to 40, 41 goes here, then 41 goes here, 44 comes here, and so on and so forth. Okay. All right. So we are set to go. So we are going to change this. So we did all this stuff, right? So we change this to true. Where were we? Change this to true. We have that error, and we fix that error. But before we fix the error, let me say something. We are going to add a sum. So we'll make a box. So we are going to sum up how many converges we had. So we are going to have, we have 46 rows. So when that number becomes 46, we know everything has converged, right? So let's box it. So we change this to true. We are going to go file, options, formulas, manual, no recalculate, enable iterative calculation. Okay. So obviously it has already done one calculation. If I press F9, 2, 3, 4, 5. In fifth, everything converged. Okay. So that is our solution. So let's plot it. So we are going to plot theta versus phi. Now, if I plot it here, what will problem would be that if this value changes, my plot is going to change. So what I'm going to do is I'm going to take all of these values. This is my final answer, and I'm going to copy and I'm going to paste spatial values only. So these values don't change. So if I do something here, I don't want my plot to change. So I'm going to plot theta versus phi. So I'm going to hold down the control key insert, and I want smooth curve. So here is my plot. Let's move it to a new sheet. And too many digits here. Let's make it format axes. Let's make it 0 digits. Okay. This is okay. Let's make it just go to 360 degrees. Also, I like my multiples to be kind of 30 degrees. So let's make it 30 here. Maybe 60. 60 is okay. Yeah, 30. Okay, let's give some titles, etc. So we always start with chart title. So this is theta versus phi. Okay, axis horizontal is theta in degrees. Vertical phi in degrees. Okay, and let's stick it back under the table. So move chart, object and slider, and put it under the table. Okay, so we have done our first part. Okay, so notice it's a slider crank mechanism. It only goes from 40 to about 100, back to about 30 and 40. So it just rocks as theta rotates 0 to 360 degrees. Okay. So we are going to hide all of these columns because we have done the parametric study. All right. So our next problem is to find these derivatives, right? So for derivatives, we need these formulas. So we need, for the first row, we need forward difference derivatives. So here is order h square relations for first order derivative, second order derivative, forward difference. Then for remaining rows except the last, we are going to use central difference, first derivative, second derivative. Backward difference, first derivative, second derivative. This would be at the last point. Okay. And then, if we multiply this by omega, we'll get d phi dt. Multiply this by omega square, we'll get d square phi dt square. So let's invoke our first derivative forward difference. So it requires h, and it requires y1, y2, and y3. Let's do forward difference second. It requires h, and you can see it requires y1, y2, y3, y4. So y1, y2, y3, y4. Okay. Next, we want central difference. So we go central difference 1. It requires h, and y1, which starts from here, y2, and y3. Okay. Central difference 2. It also requires y1, y2, and y3. All right, let's take both these and copy them to all but the last one. Okay. Now it seems like we are still in manual mode. So let's go back, check. We shouldn't be in manual mode. We should be in automatic mode. Okay. So we know we have problems, right, with our previous table. So we don't worry about it because remember, these values shouldn't change. Okay. So we have gotten all but the last one. So in the last one, we will put in our formula backward difference 1 h, and it needs 3, y1, y2, y3. So we start counting y1, comma, y2, comma, y3. Okay. Then we have backward difference, second derivative, h. It requires 4 y values. So we'll start counting y1, y2, y3, y4. Okay. So we have first and second derivative. So these are the things we typed just now. So we are going to now multiply omega times first derivative, omega square times second derivative. And I'm going to copy these down. So now we have our angular velocity and angular acceleration, right? So we can plot it versus theta. So we can take theta and we can take phi. So hold down control key, phi. Hold down control key again and select both of these columns. So we are going to plot phi dt, d square phi dt square against theta. Okay, so insert, and we want smooth curves. So here we get, move to a new sheet. And as before, let's adjust our angles, format axes. Of course, this doesn't go beyond 200, minus 300 to 200. So let's make it minus 300 to 200. All right. And we want 0. Okay. X-axis, remember we wanted 30 degrees, right? 0 to 360. And we like 30 degrees. That's pretty much it. Let's give some chart titles. So phi, let's just call it angular position, velocity, and acceleration. Okay, our horizontal is theta in degrees, and vertical is position in degree, velocity in degree per second, and acceleration in degree per second, right? Let's also move this legend kind of up. We are good. Move it back to our sheet, and we are going to drag this down. Let's drag this down. Okay, that's all we need to do. So you can see let's unhide all our rows. What did I do? Unhide columns. So remember, we did a parametric study. We solved for phi, and then we took derivatives, numerical derivatives, to solve for velocity and acceleration. What you're going to do in the next lab, lab number 10, you're going to do all of this, and then to find out how good are these velocity and acceleration values, how many digits can you depend on? Right now I'm showing lots of digits, but I don't know how good they are. So you're going to do Richardson extrapolation and find out how good your answers are.